the line is divided by Socrates as such that the two middle sections of it, the mathematical and the physical section, things must be equal in length. Here's a proof. The four parts of the line are A, B, C, D. We're given that the whole upper part is to the lower part, and it's cut in the same ratio as each of the parts. So A plus B over C plus D equals A over D equals C over D. That's what we're given. I'm trying to prove that B equals C. That is, the mathematicals and the physicals are equal. So here's a proof. Starting with this as part of the given. You can go from A over B equals C over D to A plus B over B equals C plus D over D. This is justified in Euclidean, in Euclid Book 5 by a thing called componendo. These are proof of languages proportional and also proportional componendo. Easier, just add E over B to this side and D over D to this side. They're each equal to 1, so we're adding equals to equals. It's all kosher. Then we can, what Euclid would call alternate the ratios, alternate the proportion. From this follows if we take this to this and this to this, proportionality is preserved. So with algebraic manipulation, you can do that. Results in the same thing. But we're given that this is equal, so A plus B over C plus D is equal to B over D. But A plus B over C plus D is also equal to A over B. So B over D, did I get this right?
Yeah,
okay. Did I make it?
You're fine.
Okay.
It follows from the last part of the given.
All right, yes, equals substituted for equals, the results are equal. So B over D equals C over D. Magnitudes in the same ratio to the same are equal. So if B over D equals C over D, B equals C. QED, we're done. All right? So this is a proof that shows if we cut the line in the way that Socrates tells us to, the middle two sections of the line have to be the same length. So here's the Cartesian revolution. You fold those two middle sections. Here's our line. You fold it so that these two come into coincidence. So it looks like this. A, B, C, and D. So this then is one. Okay, this is the Cartesian picture. All right. The fourfold line now looks to have three parts, with the coincident middle part upright at right angles to the extreme ends. The upright part, which brings the Platonic line's mathematical and physical segments into coincidence, represents mathematical physics. In this picture, the mathematical, the physical, and the intelligible are all the same. Math is intelligibility. No non-mathematical forms lie beyond. This may be due to an extension of the mathematical, or a truncation of the intelligible, or both. Further, the physical and the mathematical are the same, whereas for Aristotle, matter is the indeterminate stuff out of which things are formed. For Descartes, matter is geometrical extension and so perfectly knowable. All real knowledge lies along that mathematical physical line. Philosophy to become wisdom must become science, and science must become mathematical. As Kant says, there's just so much science in a subject as there is mathematics in it. Unlike in Plato, where math is subordinate to dialectic, here math has no master. Math is not the way into philosophy, it is the way out. Philosophy is the childhood of the intellect. Mathematics is philosophy grown up. Now, philosophy is often reproached for having made no progress. The same problems, the same disputes, the same sheer failure, someone says. This is false if we take philosophy to encompass all systematic rational inquiry, a sense preserved in the PhD degree, the doctorate of philosophy. In fact, as domains of philosophical inquiry succeed, they are renamed sciences and split off from what we now call, in a narrow sense, philosophy. Philosophy succeeds when it becomes mathematical. Let me very quickly trace through some history of these successes. In the ancient Greek world of Plato, math and astronomy were already distinguished from philosophy in the narrower sense. In the Platonic dialogue Theaetetus, the character Theodorus is a mathematician. He says that in his youth he studied philosophy, but growing tired of mere words, he turned to mathematics. The ancient astronomer Ptolemy says there are three theoretical disciplines: theology, physics, and mathematics. But theology is guesswork. Physics concerns sensory qualities too unstable to be known. So only mathematics, which includes astronomy, is genuine science. In the 17th century, physics becomes a science through the work of Galileo and Newton, among others, who transformed physics by mathematics. Galileo says the book of nature is written in mathematical characters. It advises us to stop looking for natural causes and start looking for mathematical relations. Newton applied the calculus that he invented to the nature that he conceptualized. His great work is titled The Mathematical Principles of Natural Philosophy. 17th century natural philosophy wanted to be mathematical, mechanical materialism. Gravity was a problem for mechanism. Newton's gravitational formula disclosed no mechanism. By the end of the 19th century, mechanism was again in trouble, as Maxwell had discovered equations for electricity and magnetism, but couldn't find a mechanical model. So mechanism was given up. As Hertz said, Maxwell's theory is Maxwell's equations. In the 20th century, quantum physics made it hard to know what materialism is. So it too is given up, and quantum theory becomes whatever is predicted by its mathematics. So one part of natural philosophy became mathematical physics, both the success for philosophy and the loss to it. Consider another part of natural philosophy, biology. In Darwin, 19th century, biology is largely natural history. The early 20th century new synthesis of evolution and genetics made biology look more mathematical, like a natural science. Take an instance, the Hardy-Weinberg law in genetics. When a gene has two alleles, one dominant, one recessive, the law shows mathematically that with no mutation, large population, random mating, and no selection pressure, gene frequencies will remain unchanged. If we take evolution simply to be change in gene frequencies, the Hardy-Weinberg conditions for stability suggest mechanisms for evolutionary change: mutation, random drift, isolation, sexual selection, and natural selection. Vague talk gives way to math models. It is no accident that two founders of the new synthesis contributed to its math. Sewell Wright invented path analysis, and Ronald Fisher made huge contributions to statistics. Moral philosophy, once the consort of natural philosophy, became psychology, economics, and political science. Let's see how math helped turn each of these into a science. Now, psychology, it is said, has a long past and a short history. The history as an empirical science dates officially from 1879, when Wundt established a psychological laboratory. Before that, psychology was part of philosophy, as psych majors discover when they study history and systems. Psychology as science, not as cure of souls, tried to become respectable by becoming mathematical. The success of psychophysics and the failure of behaviorism both came from trying to find simple mathematical functions relating world to mind. The successor of behaviorism, cognitive science, was deeply influenced by computers. The slogan in the 1960s was, "Mind is to brain as software is to hardware." Now, a computer program is a mathematical object. If you are your mind, and your mind is a computer program, then you are a mathematical object. So when the Delphic Oracle says, "Know thyself," it means learn computer science. Economics, for good and ill, has become increasingly mathematical. The trend is shown in three texts. Adam Smith's 18th century Wealth of Nations has no math. Marshall's late 19th century Principles of Economics splits the math in an appendix. Samuelson's mid-20th century Foundations of Economic Analysis splits the math front and center. Why replace prose by equation? The following tale suggests one motive. Philip Wicksteed, a late 19th century economist who used math